Assalamu alaikum, everyone. Welcome to another session for Tripoli 6311. So the last class and the last recording, actually, we discussed about the economic load dispatch, a variant of economic load dispatch, basically, where we considered, besides the minimization of the generation cost, besides that target, we also included the issue of environmental concern. Okay, so we try to minimize the cost of generation. Of course, in that case, we considered that all the generating plants are thermal in nature, so conventional fossil fuel based power plants. And then we said that, well, if we update our target of ELD just by introducing a new target of minimizing the emission also. So how can we deal with this kind of problem, which is in general known as combined economic emission dispatch? So that part is done. And now we will shift our focus to a new topic, the next topic in our syllabus, that is optimal power flow. So let's dive into the topic of optimal power flow. So in this lecture, we will go through some parts. So the first one that we will cover, we try to cover, that is what is the motivation behind discussing this topic of optimal power flow. This will be a few slides, 1 or 2 slides maybe. Then how we are going to formulate, that is the mathematical formulation for OPF. And next we will shift our focus to specifically the DC type of formulation for OPF. In short, we will call it DC OPF. So DC optimal power flow. This is one variant of the original AC optimal power flow. And we'll before starting the formulation of the DC optimal power flow, we'll also discuss why we are shifting our focus from AC optimal power flow to more specific one like the DC optimal power flow. And then we will go through the solution techniques, and we will adopt for this course, we will be adopting the solution by relaxation method. And after discussing that, we will take one example for clearer understanding of the steps that we are going to follow. So while discussing all these points in this presentation, we will shift a little bit from this slide to a different set of slide, which is where we covered basically the DC power flow, the DC load flow. So the DC load flow will be essential in solving the DC OPF actually. So while we will progress through these points in this slide, like motivation, basic formulation, and then we will shift our focus to DC power flow, which is the background or backbone of the DC OPF. So once we cover that slide of DC load flow, then again we will come back to this slide and we will start the solution by relaxation. Okay, so let's start with the motivation. So in the economic load dispatch, what we observed is that our target was to minimize the cost of generation, where the cost of generation was basically represented by CI. Okay, so CI was the cost of generation, and okay, so in this cost of generation, in this case, the individual generation cost was CI, and the total number of generation, if we consider that there is L number of generating units in our power system. So this is the total cost, and our target was to minimize the cost, and F was the cost function. And then we also discussed about the associated constraints for solving the basic economic load dispatch problem, where the constraint was simply considered as the summation of all the generations. So GI summation, G stands for the real power generation for L number of units. So this is the total generation here. Then this was the demand, real power demand minus the transmission loss, T loss. And this was represented by an equality constraint. whereas there were some inequality constraint in terms of the maximum limit and the minimum limits of individual generating units. So this was the objective, this was the equality constraint, and these were the limits. So after considering the loss as well as the inequality constraint, the problem was basically formulated as some constraint optimization problem with inequality, both inequality and equality constraints. So this was the target, and we also had to make sure, well, this is the line, also to make sure that our limits of generation outputs are within the operation limits. But if we want to obtain few more information from our power system network, then there are, as a power system operator or power system planner, then we have to think beyond this economic load dispatch. By this I mean just simply thinking about the minimizing the cost of generation may not be enough to provide us few more knowledge or knowledge about few more variables of our power system network. For example, if we want to find out, let's see, if we want to find out the information about a dispatch which will or which could provide the minimum D loss, this could be our target. So that means instead of considering this cost function, we may also define our target as a power system operator. We may also modify this target of minimizing the cost of generation. Instead of that, we may also want to look at a different solution with a different target, and that is to minimize the loss, real power loss in the network. And again, we have to remember that in a real power system, conventional power system, the power that is flowing through the network is AC in nature. So in the ELD, conventional ELD, only dealt with the real power. This is basically PD, the P demand, and this is basically the PGIs. So these are the PGIs, the PGI max and PGI min. So what I mean, in ELD, we only focused on the real power scenarios, the real power flow, the real power generation limits, the real power demand, the real power loss, the real power flowing through the lines, etc. So other than that, we also have another counterpart for real power, and that is the reactive power. So what should we do if, let's say, we want to focus on QGs? In this formulation, we cannot make sure that this is achieved. So we are not bothering about this, remember. So this is summation of I equals 1 to L. So in the classical ELD problem, we don't bother about this issue. We do not think about this issue. We also do not think about this issue. That means the limits associated with the reactive power output of the generating units. So if we think well, so this is QGI min, this is QGI max. So we also don't bother about this. So there are different issues that may come into picture as a power system operator or a power system planner. That means beside knowing only about this few information, we may also want to know the information about many other variables present in the power system network. So thus, we can look at the power as a power system operator, we may look at the operation of the power system from a different perspective. So let's see what are the other things that may come into picture. So for example, if we want to get the information about the losses, okay, so the losses can be modeled, and losses can be also minimized, which I just said. So before minimizing the losses, we also have to think about modeling of the losses. And by losses, we mean by this loss, we may refer to the P loss as well as the Q loss. So when we say that we want to focus or we want to obtain the information about the P loss and the Q loss present in the network, we can change our equality constraint a little bit. And instead of simply saying that, well, PGI minus, okay, summation of PGI minus P demand minus P loss equals to 0. Instead of saying that, we may go for a more conventional set of power flow equations like this. So the P injected in general, this we have already studied in our basic power system analysis course. So P injected in general at any bus can be represented by P generated at that bus minus P demand at that bus, and that is expressed in terms of the bus voltage magnitude of the interconnected buses, VI and VJ, and then the admittance matrix entries, absolute of that is Yij, and then the cosine multiplied by the cosine of theta I. Theta I is the angle associated, phase angle associated with the bus voltage I, minus theta j, which is the phase angle associated with the jth bus, minus delta ij, which is the phasor angle of the admittance under consideration, that is Yij. And here we have a summation j equals 1 to n number of buses. And similarly, by the entire set of power flow equations over here, what we mean is this. Besides this, we also have the expression of the reactive power. So that is Qi equals Qgi minus Qdi. And then we have a similar kind of expression, but instead of cosine, we end up with some sine expression. So the sine entry, sine will come here. All the other things will remain as it is. So this is the general expression, general power injection expression that we have already studied in earlier courses of power system. So when instead of considering this kind of equality constraint or this kind of power generation and demand and loss balance equation, we can always say that, well, instead of doing that, we have an option to go for the full power flow equation or the more conventional power flow expression at a certain bus. And once we do that, you see that automatically when we solve the full AC power flow analysis, then the loss part is always taken care of within the problem itself. So instead of going for this kind of expression, we may also go for this kind of more generic expression. And as I just said, that it is also possible to further impose limits. I mean, in the ELD, with respect to ELD. So all these statements are with respect to the conventional ELD. In the ELD, we are imposing limits only on PIs, only on the PGIs. This is our main concern in conventional ELD. Besides that, we may also want to set limits in our solution, set limits for the reactive power, generated reactive power, or the apparent power outputs. We may also impose limits on the voltage magnitudes. In general, the voltage magnitudes at any bus are limited by a certain standard, and that is in per unit between 0.95 to 1.05. So this kind of limits could also be imposed at certain generation and load buses. We may also impose limits on the line flows that is appearing throughout our network in each of the lines, because as we know that each line is designed for carrying a certain amount of real power as well as reactive power. So we may also want to include those limits into our solution. And besides all these introduction of additional limits into our solution, as a power system planner, we may also want to look at the situation when the network is under some sort of contingency. So by contingency, I mean when there is any kind of fault, or due to the fault, we have lost a certain number of generating units, a certain number of transmission lines are out of order, or those are being operated by the circuit breaker, so they are not in operation. So these are the contingency conditions. And in those contingency conditions, what will be the response of our system? How will the power flow change? Or will these contingency conditions, that is absence of a line or absence of a big generating units, will it cause any trouble to the network? So this kind of constraints, we term them simply as the security constraints. So that means if we can somehow deviate from the conventional ELD problem, there are many different scopes available to us, which will give us some additional information which are not possible to obtain through the conventional ELD problem. So how will actually this be modeled, or what are the additional variables that will help us to achieve our goal? So there are some list of variables. Which we will term them as the control variables. Okay. Term them as the control variables. These control variables we didn't discuss actually for the conventional ELD problem. In the conventional ELD problem, we only talked about the decision variables, which were the PGIs, if you remember, and lambda. Okay, our main concern was the PGIs. So we kept on varying the PGI. This is for conventional ELD again. And lambda came into picture because of the presence of the equality constraint. So the Lagrangian multiplier lambda became another unknown. But the initial problem statement, lambda was not there. So in the initial problem statement, our target was to simply obtain the different values of PGIs to minimize the cost of generation. So there is also a scope. There is also a scope for introducing a different set of control variables if we want. And if we want to look at the ELD issue from a different perspective, as a different optimization goal, with a different optimization goal. So in those cases, we may also think about, besides the PGIs, okay, PGIs is already there. Besides the PGIs, we may also think about the generation voltage magnitudes. The transformers are there in the network, so the tap setting of the transformer, and the tap setting basically plays with the magnitude of the transformer. So if this is the tap, let's say, so if I take the complete set of winding, so the voltage output at the secondary will be simply N2 by N1. The full N2 here, full N2 will come into picture if this is N2, this is N2 and this is N1. However, if I take this one, if I take some reduced number of N2, then accordingly the voltage output at the secondary will be reduced. So in this manner, we can play with the tap position of the transformer, and we can, if required, we can control the voltage. This could be another control variable. And this plays only with the magnitude of the voltage. Similarly, there is another concept of the quadrature booster, or another name is the phase shifting transformer. In those cases, because this is AC voltage, the secondary as well as in the primary in the conventional power system. So in this case, we can also play with the phase angle of the voltage that is available here, the secondary of the transformer. Then we may also think about the presence or inclusion of some sort of switched capacitor. So the switched capacitor, basically what it does, this is a variable capacitor, but variable in a discrete manner, not in a continuous manner. So these are basically used to control the line flow or control the reactance of the line. Okay, so once you can control the reactance of the line between two buses, then of course you can control the real power flow of the line. Okay. So the switch capacitor setting, this could be another control variable. So in short, by including any of these, we can also think about a different sort of optimization problem. So the power system operation could be also thought of as a different kind of optimization problem. by considering a different set of control variable other than only the PGIs that we did in the ELD. So with all these motivation, now let's go through the definition of OPF. So what is OPF? The optimal power flow. It is the power flow problem. So we can say it is the power flow problem. So by power flow problem, we mean it is in the OPF itself. We are still thinking about the power flow problem, means the load flow problem. This is the basic load flow problem. So we think about the load flow problem. Remember, we just talked about the PIs and QIs. So these PIs and QIs are basically part of the load flow equations. So the PIs and QIs, we are talking about these injections, which are of course function of generation and demand, and ultimately it is function of the bus voltages, the admittance entry, admittance bus admittance matrix entries, and the associated bus voltage angle or the bus voltage angle phasors, as well as the admittance angles. So the power flow problem, it is still the power flow problem, but there is a little difference. In the power flow problem, we didn't think about any sort of optimization. The basic power flow problem, we didn't think about any sort of optimization. So what we did there is simply, so in the load flow, we don't think about any sort of optimization. So we just think about fulfilling or satisfying this expression of the equality that could be achieved for this PI and the QIs, PGI minus QGI, sorry, PGI minus PDI, and QI is QGI minus QDI. So our basic target is to change this PGI and QGI and try to achieve this balance and this balance. And how do we change these PGIs and QGIs? As we showed there, this is some function of voltage magnitudes, and of course Y bus entries, these are constants, and there are some associated angles, theta and delta. Similarly, this is also some function of the voltage magnitudes, the admittance entries, the phase angles of the bus voltages, and the angles of the admittance. So by varying this V, magnitude of V, by updating the magnitude of V as well as the angle theta, okay, by playing with this V and theta in an iterative fashion, what we try to change this PGI. We try to find out this PGI, this QGI, and try to establish the balance. We can say in one way, this is our equality constraint for conventional load flow or conventional power flow problem. So in this case, we do not think about or do not introduce any sort of optimization issue. So the basic difference between the OPF, optimal power flow, and the conventional power flow lies in the fact that in the optimal power flow, we must think about some sort of optimization. And this optimization should be done, of course, by satisfying some constraints. And because this power flow issue is associated with the network, power system network, and each component has its own limits, operational limits. So the optimization will be done keeping an eye on these constraints, which are commonly known as the network constraints. So when the conventional load flow issue is solved with a target to optimize some sort of objective function, satisfying some sort of network constraints, then we call that kind of load flow problem, we term it as the optimal power flow or optimal load flow problem. In short, we call it OPF. So what are the features? There are some features of the OPF, or very different types that we may adopt for solving the OPF. So this is the statement. We calculate the optimal generation dispatch. So this is the example where the objective is the same as ELD. Okay, so this is the objective of OPF. So we calculate the optimal generation dispatch as well as the control variables. So by control variables, we may also, in terms of optimization, we may call it the decision variables. So we change the decision variables. We calculate with those updated decision variables, different values of decision variables, we try to achieve the minimized operational cost, okay, for this amount of generation dispatch. And we also try to satisfy all kind of transmission system limits, all transmission system limits. So we vary, in short, we vary the control variable. Our target could be, there could be different targets, but here in this definition, we are still mentioning the target of the conventional ELD. So the target here is still minimizing the operation cost, which is same as the ELD. The decision variables we have to vary, and we have to find out the optimal generation dispatch. That means the output of each of the generating units. However, in the OPF, we may also look out for the by generation. Here we may include, besides the PI, which is already taken in ELD, we may also think about QI. So we can add this besides PI. So this is the change. Meeting all transmission system limits. So remember, in the ELD, the limits that we considered in the conventional ELD, the limits were only imposed on PGI. Okay. In the optimal power flow, the choice, there is variation in our choice, or the choice, the number of limits we can impose is increased compared to the conventional ELD. So this is for ELD. For OPF, besides that, we can also incorporate limits on QGIs. We can also incorporate limits on the line flow, that is the apparent power flow in the lines. We can also impose limit on the bus voltage generation magnitude. So these are the few examples where the ELD is different than the OPF, or the OPF is different than the ELD. OPF is a much more complex problem compared to the conventional ELD. Okay, so, and besides that, there is other variations. This is the basic statement of OPF, the first one over here. The other choices could be that by OPF, we can also look for including some of the security constraints, and we may plan beforehand for a preventive dispatch. Means we may think, or we may forecast that, well, the weather is not good enough after 1 month, so there could be storm, and because of that there could be some issues, weather issues, and some trees might, the branches of some trees might fall over some of the transmission lines, long transmission lines, so the operation would be hampered. Or there could be some maintenance issue, let's say some regular maintenance or routine maintenance issue for a certain number of generating units on a specific time of the year. So those generating units would not be available. So how should we redispatch, or how should we design our dispatch in such a manner that none of the security issues are violated? By the security issues, we mean that none of the lines are overloaded. So the S line, the line flow is within the limits, the voltage magnitudes are within the limits. And besides the line flow, we can also tell about the P line is within the limits, or the I line is within the limits, all the same. So this is the preventive dispatch, means before the issue occurs, before the problem occurs in the power system, we plan beforehand, and we design our dispatch, we decide our dispatch in such a manner that we are in a preventive mode. Okay, we do not want the problem to occur. So this is preventive dispatch. On the other hand, the corrective measure, the corrective dispatch is in case of emergency situations means any kind of issue, any kind of contingency that occurred that was not planned beforehand. So, and that came into picture because nothing is actually in our hand completely. So some scenario came, which some emergency situation came due to some non-credible uh, fault. By non-credible, I mean which was not pre-planned, okay, or which some maintenance is required, which was not pre-planned, okay. A sudden storm came into picture, which was not which we couldn't actually forecast beforehand, and due to that there was a huge gust of winds, and because of that some of your transmission network has been damaged to an extent that you are unable to supply the power through those networks. So what you would do, so the corrective dispatch, the corrective measures are taken after the problem has occurred. This is in the emergency situation, whereas the preventive dispatch is planned, pre-planned, okay. So in that time, when that time of the year comes, so what you do, you simply follow your routine work that, well, now your dispatches should be made following this schedule. Okay. Okay, so, and then there could be other choices of OPF, like we may want to look at the maximum stress the system can take. That is the maximum loadability issue. And there could be other choices like determination of bus incremental cost by considering some different kind of power system economic analysis. So these are the some of the this is the definition of OPF basically, and some of the different applications where we may see the necessity of OPF or optimal power flow. So with all these, now let's have a look at some of the variables and some of the parameters that will come up while we will try to solve the OPF problem. So let's see the next slide. So we have some control variables, some state variables, and some parameters. So in the power system, the control variables are those which you can directly control. Okay. For example, in this case, the control variables, the human or machine intervention can be done. So some example could be the generation set point. This is one example. The tap changer position, another example. The reactive power output from, let's say, some FACTS device already installed in your network. This is, you can do it directly. So you can directly control, you can directly change or maneuver these variables from your end as a power system operator. And once you change those things, this basically provides you some sort of degrees of freedom to optimize the power system operation. So these are the control variables. Next, and we denote it by the vector U. Then comes the state variables. In this case, this you actually cannot act upon as a human being, or you cannot act upon through the machine intervention. Okay, some of the examples are the bus voltages. Okay, the line flows. You cannot control directly the line flows. You cannot control the bus voltage directly. Okay, rather what you can do, you can the bus voltage, you can change the excitation, okay, the excitation input, and accordingly you may be able to control the bus voltage. The line flow is basically the function of the bus voltage, basically the bus voltage magnitude as well as the bus voltage angle. Okay, so the magnitude might be possible. The magnitude might be possible by changing the excitation. However, the angle, this is not possible directly. Okay, so similarly, the line flows between two buses. You have one bus and two bus I and J. So what I mean, probably you will be able to control the magnitude, but the associated phase angle you cannot control directly by the excitation system. So similarly, this is Vi theta I, this is Vj theta j. So these things are not possible. And thus the flow the line flow, the power that is being flown between this bus and this bus, you cannot directly control them. Like you can directly control the set points or the tap changers or the reactive output. Okay, this is direct control. However, these are indirect control. Okay, so these are indirect control. So these are the state variables, and these are the output. So this can be controlled basically by the control variables. So the state variables are controllable by the control variables. So there is a direct link between these two. And these state variables, we define them by the vector x. And the last set of thing, these are the parameters. These are the constant parameters already provided to us, given. It is already known beforehand, like the generation cost. Okay, by the generation cost, I mean, let's say if it is a quadratic function, so we should know these coefficients, ai pgi squared plus bi pgi plus ci. So these coefficients should be known beforehand. The transmission line parameters are an L or XL, whatever, and then XC. So the shunt susceptance, these values should be provided to us. So these are the technical and the economic issues, the technical parameters and the economical parameters that are more or less constants. So we call them as the parameters, and that is denoted by the vector y. So these are the things, these are the parameters and variables that will come up when we try to solve the conventional OPF problem. So we have, in short, we have some control variables which we can control directly, some state variables which we cannot control directly, but through the control variables we can have some sort of controllability over those. And then the third set is the parameters, which are more constants. So this is the basic mathematical formulation for the OPF. Our target is to minimize, again, minimize some sort of objective function. Here we are expressing it in terms of f, and this is function of all three kinds of set of parameters. I mean, it is the function of the constant parameters, the function of the state variables x. It is also the function of the control variables u. And the optimization will be achieved by changing these control parameters. So the control parameters, you can also name them as the decision variables for our optimization problem in case of OPF. And besides this basic objective function, we also have to satisfy some equality constraints as well as some inequality constraints. So I have already mentioned the set of equality constraint and the set of inequality constraints. So I don't think this part has to be covered. Just please go through this last few lines and think about some examples of constraints on control variables, an example of constraints on state variables, as well as some example of the equality constraint and the example of inequality constraint, as well as the example of the objective function. And this is the basic ACOPF. And if we want to deviate from this ACOPF, we will come to the variant or a simpler version of the OPF problem that is known as the DCOPF. So in the DCOPF, you see the decision variable now changes. Instead of a U vector, we only have to think about, again, in the DCOPF, you only have to think about the PG. Okay, so the PG is our decision variable here. And the function, the objective function now becomes the vector of PG and some parameters, constant parameters. There is no state variables, directly no state variables. Or in other words, you can say the state variables or the control variables are merged together like as a set PG. And the equality constraint, we have specified it like the P generation minus the P demand minus some notation that is B dash and theta equals to 0. So the generation minus demand minus P B prime theta equals to 0. So what we can do here later on, when we will formulate the DC load flow, we will show how and why this is actually appearing here. Okay, what is this and how it comes. So For the time being, just we get to know that the equality constraint is between the real power generation, the real power demand, and some matrix multiplication, matrix vector multiplication. So this B prime, we will see later on, is a matrix, and theta is a vector. Okay, so matrix into vector ultimately will yield a vector. By vector, I mean an array. The dimension of this array should be the same as the dimension of PG as well as PD. So we will see it later on. And the inequality constraints, you see here we have PGs. This is our precision variable. Theta, this is the bus voltage angles, and this the parameters. So the inequality constraints, one example could be the line flows. Here you see the line flows, and generation dispatch constraints. Means PGIs, again, all the same. PGI mean like the conventional ELD. Again, PGI is, it should be lying in between PGI min and PGI max. This is about the generation dispatch constraints. Line flow constraints, S line should be less than S line max. And the equality constraint, these are about the inequality constraint. The equality constraint, this is known as the DC power flow equations. The first one is basically the DC power flow equation. The AC power flow equation, I just wrote it a few slides ago, PGI minus PDI, which is some function of some network variables, voltage, bus voltage magnitude, bus voltage angle, admittance, as well as the admittance angles. So this is AC power flow equation. However, this one here over here is the DC power flow equation. So whatever we are getting here, a similar kind of flavor will be obtained here in the equality constraints. We will see later on, inshallah. So up to this point, we have clarified, or we have discussed about the motivation of OPF and the formulation of OPF. By simply OPF, we mean this is the AC OPF. And when we specifically say DC OPF, that means in this case, the formulation will look more or less like this. So now from this point, we will shift our focus a little bit to a different set of slides, as I mentioned at the beginning of the class. So now we will see what is basically the DC power flow, because you can clearly see that the DC power flow equation, is a part of the DC OPF solution. So let us see now what is basically the DC power flow and how actually we will get it simply by by the application of some simplifying assumptions to the AC power flow expressions. So let's switch our focus to next set of presentations. So this is